At 4:12 UTC, NASA's Deep Space Network flagged an anomaly, a routine photometric update on 3I Atlas, the third known interstellar object, suddenly spiked across multiple wavelengths. The pattern was too clean to be random, and for the first time, someone inside NASA wrote the word engineered. The discovery didn't arrive with fanfare, no press conference, no carefully worded statement from the administrator's office. It came as a flagged data packet from the Goldstone Deep Space Communications Complex in California's Mojave Desert, routed through 3 validation servers before landing in the inbox of Dr. Sarah Chen, a spectroscopic analyst who had been tracking 3I Atlas since its orbital parameters first appeared in the Minor Planet Center's database 14 months earlier. She had been expecting another routine confirmation of the object's trajectory, perhaps a minor adjustment to its ephemeris. What she received instead was a spectral signature that made her close her office door and call her supervisor before opening the full dataset. The object that would come to be designated 3I Atlas, following the nomenclature established after Oumuamua and 2I Borisov, had entered the inner solar system along a hyperbolic trajectory that immediately identified it as extrasolar in origin. Its velocity relative to the local standard of rest exceeded 42 kilometers per second, too fast to be gravitationally bound to our sun. It had come from elsewhere, from the vast dark between stars, and like its predecessors, it was merely passing through our neighborhood on a journey that began long before humanity learned to make fire. But unlike Oumuamua, which had tumbled chaotically through space, reflecting sunlight in erratic bursts that suggested an elongated, possibly fragmented body, and unlike 2I, Borisov, which had displayed all the expected characteristics of a conventional comet complete with a well-behaved coma and tail, 3I Atlas moved with an unsettling consistency. Its light curve, the graph of its brightness over time, showed variations, yes, but variations that repeated with mechanical precision. Every 4.73 hours, down to the millisecond, the object completed one rotation. The precision was remarkable. Natural bodies tumble. They precess. Their rotation periods drift, as outgassing jets provide asymmetric thrust, as tidal forces from nearby gravitational wells exert their influence, as the simple chaos of an object that has been colliding and fragmenting and reforming for billions of years expresses itself in irregularity. 3I Atlas did none of these things. It spun like a gyroscope in a vacuum chamber, and that fact alone had been enough to elevate it to priority status among the community of astronomers who study interstellar visitors. But precision alone doesn't indicate artificiality. Nature can produce remarkable regularity under the right conditions. A perfectly spherical droplet of molten metal frozen in the vacuum of space. A tidally locked body that has achieved equilibrium. There are natural explanations for almost everything, if you're patient enough to work through the mathematics. What appeared in Dr. Chen's analysis that morning in March was not something that invited natural explanations. It was something that resisted them with the force of physical law. The spectroscopic data had been gathered during a dedicated observation window using the Keck Observatory's Hires spectrograph, one of the most sensitive instruments available for analyzing the composition of distant objects through the fingerprints of light they reflect or emit. Standard procedure involves measuring how an object's reflected sunlight has been altered by absorption or emission at specific wavelengths, revealing the chemical elements present on or near its surface. Asteroids show the broad absorption features of silicate minerals. Comets reveal water ice, carbon dioxide, carbon monoxide, sometimes more complex organic molecules. Each substance leaves its signature in the spectrum, and experienced analysts can read these signatures the way a forensic investigator reads blood spatter patterns. The spectrum of 3I Atlas showed something unprecedented. Among the expected broad features consistent with carbonaceous materials similar to C-type asteroids common in the outer main belt were 3 extremely narrow emission peaks. Not absorption, emission. The object was producing light at these specific wavelengths, not merely reflecting it. The first peak occurred at 1,278.6 nanometers, deep in the near-infrared, the second at 1,534.2 nanometers, the third at 1,891.7 nanometers. Each peak was extraordinarily narrow, with a full-width half-maximum of less than 0.3 nanometers. In spectroscopic terms, this was a needle in a haystack, except the needle was glowing. Natural emission lines do exist. They're common in astronomical spectra. Hot gases emit light at characteristic wavelengths determined by quantum mechanics, by the specific energy levels of electrons transitioning between orbital shells in atoms and molecules. These emission lines are well catalogued. Hydrogen alpha at 656.3 nanometers, the oxygen doublet at 630 and 636.4 nanometers, the sodium D lines, hundreds of others, each corresponding to a known physical process in a known substance under known conditions. The three emission peaks from 3I Atlas corresponded to nothing in the spectroscopic databases, not to any known atomic transition, not to any molecular band, not to any combination of elements that might produce these wavelengths through chemical luminescence or thermal emission. Dr. Chen had run the numbers through every spectroscopic library available to her. She had consulted atomic physics tables. She had reached out to colleagues at MIT and Caltech who specialized in exotic spectral phenomena. No one could identify a natural process that would produce emission lines at precisely these wavelengths, with precisely this intensity ratio, from an object at the temperature and composition suggested by the rest of the spectrum. But the emission peaks themselves, mysterious as they were, represented only the first layer of the anomaly. It was the behavior of these peaks that had prompted Dr. Chen to close her door and make that call. Because when she had plotted the emission intensity against the object's rotation phase, matching each spectral observation to the precise point in 3I Atlas's 4.73-hour rotation cycle, she found that the three peaks weren't constant. They varied. They brightened and dimmed in a coordinated pattern that repeated every rotation with absolute fidelity. At rotation phase 0, defined as the moment when the object presented its maximum cross-sectional area to Earth based on the light curve, all three peaks reached maximum intensity simultaneously. As the object rotated, the peaks dimmed together, reaching minimum intensity at phase 0.5, when the object showed its minimum cross-section. Then they brightened again, maintaining their intensity ratios throughout the cycle. This meant the emission sources were fixed to specific locations on the object's surface or within its structure and were directional. They pointed, and every 4.73 hours, as 3I Atlas rotated, these emission sources swept across Earth's line of sight like beacons. Dr. Chen had spent 2 hours that morning running simulations, trying to construct a scenario where natural phenomena could produce this result. Phosphorescence from exotic minerals energized by cosmic rays, re-emitting stored energy preferentially in certain directions due to crystal structure. Fluorescence triggered by solar ultraviolet radiation, channeled through some unknown subsurface geometry. Thermal hotspots maintained by the slow decay of radioactive elements, concentrated in specific locations by ancient differentiation processes. Every scenario required increasingly specific assumptions, increasingly unlikely coincidences of composition and geometry and physics, and none of them explained why the emission occurred at those particular wavelengths that matched no known substance. By the time her supervisor, Dr. Marcus Reeves, arrived at her office, Dr. Chen had convinced herself that she had made an error somewhere in her data reduction pipeline. Some artifact of the instrument, some misalignment of the calibration frames, some subtle bug in the software that had introduced false features into the spectrum. She walked him through her analysis, expecting him to find the flaw, to point out the rookie mistake that would make the anomaly disappear. Instead, he sat in silence for 10 minutes, scrolling through her plots and tables, occasionally asking her to bring up a particular data set or rerun a calculation with different parameters. Finally, He asked her if anyone else had seen this data. When she said no, he told her to keep it that way until they could verify it independently. Within 48 hours, 3 other observatories had confirmed the emission peaks. The Shane telescope at Lick Observatory, using an upgraded spectrograph commissioned specifically for characterizing interstellar objects. The Gran Telescopio Canarias in the Canary Islands, whose large aperture allowed for high signal-to-noise observations of the relatively faint object. And most significantly, the James Webb Space Telescope, which dedicated 6 hours of director's discretionary time to obtain near-infrared spectra across the full wavelength range of 3 IATLAS's emission features. All 3 facilities detected the same narrow emission peaks at the same wavelengths, showing the same rotational modulation. The anomaly was real. It was not an artifact. It was a physical phenomenon, occurring at a small, frozen body, approximately 340 astronomical units from the Sun, traveling through the outer solar system at a relative velocity that would carry it back into interstellar space within 18 months. The verification data triggered a series of emergency meetings within NASA's Planetary Defense Coordination Office, an organization primarily tasked with tracking near-Earth asteroids that might pose collision risks, but which also maintains oversight of anomalous objects entering the solar system. The meetings were classified. This was unusual for astronomical data, which is typically shared openly through international agreements and professional courtesy. But the decision to restrict access came from higher in the agency hierarchy, from administrators who understood that certain kinds of information require careful handling, particularly when that information suggests phenomena that challenge existing frameworks for understanding the universe. The term engineered appeared in an internal memorandum dated March 19th, written by Dr. Eliza Constantine, a physicist who had spent 15 years analyzing data from spacecraft, studying the outer planets and their moons. Her memo was addressed to the director of NASA's Astrobiology Division and carried the subject line, 3 IATLAS Spectroscopic Anomalies, Request for Expanded Analysis Authorization. In it, she laid out a careful argument that the emission peaks, combined with the object's rotational stability and several other characteristics that were beginning to emerge from the accumulating data, suggested the possibility of a non-natural origin. She did not use the word alien. She did not speculate about civilizations or intent. She simply noted that the probability of the observed characteristics arising through natural processes appeared to be extraordinarily low, and that this warranted consideration of alternative hypotheses, including technological ones. The memo circulated among a small group of senior scientists and administrators for 3 days before someone leaked it to a journalist at The Atlantic. The leak was partial, just 2 pages of a 12-page document, enough to convey the basic claim, but not the detailed reasoning or the supporting data. The resulting article, published online at 3 a.m. Eastern Time on March 23rd, carried the headline, NASA Scientists Consider Artificial Origin for Interstellar Object. It was measured and careful, quoting the memo's exact language and interviewing several astronomers who offered cautious commentary, but the headline alone was sufficient to trigger a cascade of media coverage, much of it less measured, much of it drawing direct parallels to Oumuamua and the speculation that had surrounded that object's unusual acceleration and tumbling motion. By noon that day, NASA's Public Affairs Office had released a statement emphasizing that the research on 3 IATLAS was ongoing, that multiple hypotheses were being considered, and that preliminary findings should not be overinterpreted before the data had been thoroughly analyzed and peer-reviewed. The statement was precise and diplomatic, and utterly ineffective at dampening public interest. Within hours, 3 IATLAS had become the subject of trending hashtags, conspiracy theories, and intense debate among scientists who had not seen the classified data but who understood enough about spectroscopy to recognize that something genuinely anomalous was being reported. It was in this environment that Dr. Abraham Avi Loeb, the Frank B. Baird Jr., professor of science at Harvard University and former chair of the astronomy department, published an article on Medium arguing that the scientific community should take seriously the possibility that 3I Atlas might be an artifact of extraterrestrial technology. Loeb had achieved both fame and controversy for his earlier arguments that Oumuamua could have been an interstellar light sail, a thin reflective structure accelerated by radiation pressure, perhaps a probe from another civilization. His hypothesis had been met with significant skepticism from other astronomers, who argued that natural explanations, though perhaps less exciting, were more consistent with Occam's razor. But Loeb had persisted, pointing out that dismissing technological hypotheses a priori was itself unscientific, a form of anthropocentric bias that assumed our civilization's technological capabilities represented some kind of upper limit. Now, with 3I Atlas displaying characteristics that seemed even more difficult to explain naturally than Oumuamua's trajectory anomalies, Loeb's arguments found a more receptive audience. In his article, he walked through the emission peak data that had been made public, noting that narrowband emission required coherent processes, lasers, masers, or other technologies that could produce monochromatic light. Nature occasionally creates coherent emission through astrophysical masers, where molecular clouds act as natural amplifiers for specific wavelengths. But these occur in clouds spanning light years, not on the surface of kilometer-scale objects. For 3I Atlas to produce such narrow emission peaks, some mechanism had to be selecting those precise wavelengths and amplifying them preferentially. Loeb argued that the most straightforward explanation was that the object contained devices designed to emit light at those frequencies, perhaps as beacons, perhaps as communication systems, perhaps for purposes we couldn't yet fathom. His article included a single sentence that would be quoted and requoted thousands of times over the following weeks. When you have eliminated the natural, whatever remains, however improbable, must be considered seriously. The public discourse around 3I Atlas quickly divided into familiar camps. Skeptics argued that insufficient data existed to justify jumping to exotic conclusions, that the history of astronomy was littered with anomalies that turned out to have prosaic explanations once better observations became available. Believers countered that scientific progress required entertaining unconventional hypotheses when conventional ones failed, that the evidence should lead the conclusions rather than preconceptions. Between these poles, most astronomers occupied an uncomfortable middle ground, genuinely puzzled by the data but professionally cautious about stating anything definitive in public. What the public didn't know what remained within the classified portions of Dr. Constantine's memo and the subsequent internal reports was that the emission peaks represented only one data point in a constellation of anomalies surrounding 3I Atlas. The full picture was stranger than the partial leaks suggested, and it was this full picture that had prompted the unprecedented decision to sequester certain data sets and retask multiple space-based and ground-based observatories toward a single object in the outer solar system. The second major anomaly involved the object's thermal signature. All objects above absolute zero emit thermal radiation according to their temperature, a continuous spectrum of light predicted by Planck's law of blackbody radiation. The peak wavelength of this emission depends on temperature. Hot objects glow blue, warm objects glow red, cool objects emit primarily in the infrared. By measuring an object's thermal emission across multiple wavelengths, astronomers can determine both its temperature and its emissivity, a property that describes how efficiently it radiates heat compared to an ideal black body. 3I Atlas's thermal emission was peculiar in several ways. First, its temperature distribution showed unexpected symmetry. Most solar system bodies, when illuminated by the sun, develop temperature gradients. The side facing the sun warms up. The side in shadow cools down. Rotation helps average out these differences, but there's always some asymmetry, some hot spot that lags behind the subsolar point due to thermal inertia, some cold spot that takes time to warm as it rotates into sunlight. These thermal irregularities appear as phase-dependent variations in infrared brightness. 3I Atlas showed almost no such variation. Infrared observations from the Spitzer Space Telescope's archival data gathered before the telescope was decommissioned revealed that the object maintained a remarkably uniform temperature distribution across its surface. At any given rotation phase, the infrared emission remained constant to within 2%, suggesting that heat was being distributed efficiently throughout the object's structure. This implied either a composition with extraordinarily high thermal conductivity, allowing heat to flow rapidly from warm regions to cool ones, or some active thermal management system that transported heat mechanically. The latter possibility seemed far-fetched, but it aligned with another thermal peculiarity. The object's temperature was slightly higher than it should have been at its distance from the Sun. Not dramatically higher, just 3 to 4 Kelvin above the expected equilibrium temperature for a body with its observed albedo and heliocentric distance. This excess could represent internal heat sources, either from radioactive decay or from some other energy-generating process. But radioactive decay produces heat continuously and should have been detectable as a steady background in the thermal spectrum. Instead, the excess heat varied subtly with rotation phase, suggesting it was somehow coupled to the object's spin. A third thermal anomaly emerged when astronomers compared observations taken months apart. As 3I Atlas moved outward from the Sun, its temperature should have decreased predictably according to the inverse square law of solar heating. But the temperature decline was slower than expected, as if the object possessed thermal inertia that exceeded any known material's heat capacity. It was cooling, yes, but it was cooling as if it contained some reservoir of stored heat that was being released gradually, maintaining a warmer temperature than the equilibrium with its environment should have allowed. These thermal characteristics, taken together, suggested an object with an internal structure more complex than a simple rubble pile or monolithic rock. They suggested layering, compartmentalization, perhaps internal voids that could contain insulating materials or heat transfer mechanisms. And when combined with the emission peaks and the rotational stability, they began to paint a picture of an object that was, in some sense, organized. The third category of anomaly involved the object's rotation itself, but not just its stability, its axis. Every rotating body in space possesses an angular momentum vector that defines the orientation of its rotation axis relative to the stars. For natural bodies shaped by collisions and gravitational interactions, these rotation axes point in essentially random directions. There's no preferred orientation, no reason for an asteroid's north pole to point toward any particular constellation rather than another. 3I Atlas's rotation axis pointed, with remarkable precision, perpendicular to the plane of the Milky Way galaxy. Its spin axis was aligned with the galactic north-south direction to within 0.3 degrees, a precision that strained coincidence. To understand why this was significant requires appreciating the scales involved. The Milky Way is a disk approximately 100,000 light-years in diameter and roughly 1,000 light-years thick, containing hundreds of billions of stars. From our position within the disk, we see the galaxy's plane as the luminous band of the Milky Way that arches across the night sky. The direction perpendicular to this plane galactic north points toward the constellation Coma Berenices, while galactic south points toward the constellation Sculptor. For an interstellar object to possess a rotation axis aligned with this cosmic architecture suggested one of two possibilities. Either the alignment was coincidental, a random occurrence that happened to place the axis within 1/3 of a degree of the galactic pole, or the alignment was deliberate, the result of some process that had established the orientation with purpose. The probability of the former, assuming truly random orientations, could be calculated, approximately 1 in 60,000. Low, but not impossible, objects with unlikely orientations must exist somewhere. But the alignment took on additional significance when combined with other trajectory data. Dr. Raymond Talbot, an orbital dynamicist at the Jet Propulsion Laboratory, had been running simulations of 3I Atlas's trajectory both forward and backward in time, attempting to determine where it had come from and where it was going. Tracing interstellar trajectories is challenging because even small uncertainties in velocity and position measurements propagate into large uncertainties over interstellar distances and timescales. Still, by incorporating the most precise observations available and accounting for the gravitational influences of the Sun and planets, he had narrowed down the object's origin to a region of space roughly 10 light-years across, located approximately 40 light-years from the solar system in the direction of the constellation Perseus. There were no particularly notable stars in that region. No bright suns, no known exoplanetary systems, just a scattering of dim M-dwarfs and K-dwarfs, the common red and orange stars that make up the vast majority of the galaxy's stellar population. But when Talbot plotted the trajectory in galactic coordinates rather than heliocentric ones, something interesting emerged. 3I Atlas's velocity vector relative to the local standard of rest, the average motion of stars in the solar neighborhood, was almost exactly parallel to the galactic plane. It was traveling, in essence, horizontally through the galaxy, neither rising nor falling relative to the thin disk of stars and gas that marks the galaxy's most active regions. Interstellar objects should show a variety of velocity vectors, reflecting the random motions of whatever systems ejected them. Some should be traveling up relative to the galactic plane, some down, most at oblique angles. For 3I Atlas to be moving parallel to the plane, with a rotation axis perpendicular to it, suggested a connection between the object's motion and the galaxy's large-scale structure. It suggested, perhaps, that whoever or whatever had set this object in motion had done so with reference to galactic coordinates, not local stellar ones. This was the point at which the term navigation began appearing in the classified discussions. If you were sending a probe through the galaxy and wanted to give it a stable reference frame for orientation and navigation, you might choose galactic coordinates. You might align its rotation axis with the galactic poles, providing a gyroscopic stability that would persist across millions of years and thousands of light-years. You might launch it parallel to the galactic plane, ensuring it would remain within the densest regions of stars, maximizing the probability of encounters with stellar systems. These choices would make sense for a designed object. For a natural one, they represented a series of remarkable coincidences. Dr. Talbot's report on the trajectory analysis included a section titled Implications of Non-Random Orientation, in which he carefully avoided making definitive claims, but noted that the observed alignment of rotational and velocity vectors with galactic coordinate axes suggests selection effects that are not immediately explained by standard ejection mechanisms. It was the careful language of a scientist who had spent his career analyzing the chaotic physics of asteroid collisions and planetary formation, now confronting data that seemed to resist chaos, data that seemed to prefer order. The fourth anomaly came from radio observations, and it was this data that would ultimately prove the most difficult to explain through natural processes. The detection came from archival analysis of Arecibo Observatory data, conducted by a team led by Dr. Maria Santos, a radio astronomer at the SETI Institute who had been searching for technosignatures in the vicinity of interstellar objects. Arecibo, the massive 305-meter radio telescope in Puerto Rico that had collapsed in December 2020, had in its final years observed 3I Atlas during a systematic survey of all known interstellar and unusual solar system objects. The data had been archived but not fully analyzed before the facility's destruction. Dr. Santos had obtained access to these archives as part of a research program studying radio emission from comets and asteroids, looking for correlations between surface composition and radar reflectivity. She had been processing the 3I Atlas observations as part of a larger data set when she noticed something that stopped her analysis entirely. The radar echo from 3I Atlas showed structure in its temporal pattern, a repeating sequence of amplitude variations that occurred over a period of 19.2 seconds, cycling precisely 12 times during each 4.73-hour rotation period. Radar astronomy works by transmitting radio waves toward an object and measuring the properties of the reflected signal. The time delay reveals distance, the frequency shift reveals velocity, and the spreading of the signal in frequency and time reveals properties of the target's surface and rotation. Rough surfaces scatter radio waves diffusely, producing broad, smooth echoes. Smooth surfaces produce sharper, more focused returns. Complex shapes create complex echoes, as different parts of the object reflect the radar pulse at different times. What 3i Atlas produced was something unprecedented, an echo with discrete, repeating temporal features that suggested regular structures on its surface, spaced at consistent intervals. The pattern repeated not just once or twice, but throughout the 4-hour observation window, showing exactly the same sequence of features at exactly the same intervals, rotation after rotation after rotation. This was not the echo of a random surface. This was the echo of geometry, of regularity, of something that possessed structure at multiple scales. Dr. Santos ran simulation after simulation, trying to reproduce the echo pattern using different combinations of surface roughness, shape models, and composition. She could create echoes that vaguely resembled certain features of the observed signal, but she couldn't reproduce the precise temporal spacing, the exact repetition rate, the way the features maintained their relationships across the entire observation period. Natural surfaces are irregular. They have variation. They have randomness. Even structures created by natural processes, hexagonal basalt columns, salt flats, certain impact crater patterns show variations, asymmetries, imperfections. The radar echo from 3i Atlas suggested a surface whose structures repeated with a precision that exceeded what natural processes typically produce. But the truly unsettling aspect of the radar data emerged when Dr. Santos began analyzing the echo's frequency structure. The return signal wasn't just amplitude modulated in time, it was also structured in frequency space, showing narrow peaks at specific offsets from the transmitted frequency. These peaks were caused by Doppler shifts from different parts of the rotating object, with regions moving toward Earth producing blue-shifted returns and regions moving away producing red-shifted ones. The distribution of these Doppler shifts reveals the target's rotation rate and orientation. For 3i Atlas, the Doppler distribution showed something unusual. The frequency spread was narrower than expected for a tumbling, irregular body. It was consistent with rotation about a single axis with minimal wobble, confirming what the optical light curves had suggested. But embedded within this distribution were multiple discrete frequency peaks, each representing a distinct reflecting surface with its own specific velocity relative to the observer. The number of peaks, their spacing, and their stability across multiple rotations all suggested the presence of flat surfaces or edges arranged at regular intervals around the object. Dr. Santos's report included the phrase, geometric regularity consistent with faceted structure or surface patterning. She noted that while natural crystallization processes can create faceted shapes, think of quartz, crystals, or pyrite, these typically operate at small scales and create patterns that, when viewed in aggregate across a large object, average out into smoother overall reflectivity. To create the observed radar echo, 3i Atlas would need to possess large-scale geometric regularity, structures spanning tens or hundreds of meters, arranged with considerable symmetry around its rotation axis. The report circulated within NASA and among a small group of approved external researchers. It reached the desk of Dr. Loeb at Harvard, who incorporated its findings into a technical paper he was preparing for submission to the Astrophysical Journal letters. It reached the Pentagon's All-Domain Anomaly Resolution Office, the successor to various previous governmental efforts to investigate unexplained aerial phenomena. It reached the intelligence community, where analysts began running probability assessments and risk scenarios. And it reached the Breakthrough Listen initiative, the most comprehensive SETI program in history, funded by Russian-Israeli billionaire Yuri Milner to search for evidence of extraterrestrial technology across millions of stars. Within 2 weeks of Dr. Santos's report becoming known within the relevant communities, Breakthrough Listen announced that they would be dedicating significant observing time on the Green Bank Telescope in West Virginia to conduct a high-sensitivity radio search for intentional signals from 3I Atlas. The announcement was public, but carefully worded to avoid sensationalism. They noted that interstellar objects represented unique opportunities to test SETI detection methods, that the objects' unusual characteristics warranted careful examination, and that the observations would be conducted across a wide frequency range to search for narrowband carriers, pulsed signals, or other features indicative of artificial transmission. The Green Bank observations began on April 3rd and continued for 6 nights, covering multiple rotations of the object and spanning frequencies from 1 to 12 gigahertz. The telescope tracked 3I Atlas as it moved slowly across the sky, accumulating millions of spectra, searching each for the telltale signature of a signal that stood out from the random noise of the universe's background radio emission. On April 7th, at 2:34 UTC, the detection algorithms flagged a candidate signal. It was narrowband, centered at 1.42 gigahertz, the frequency of neutral hydrogen's emission line, the most abundant element in the universe. A wavelength that SETI researchers had long considered a logical choice for interstellar communication because any civilization capable of radio astronomy would recognize its significance. The signal appeared in multiple consecutive spectra, persisting for 14 minutes before fading below the detection threshold. Its frequency remained constant to within 0.05 Hz, far more stable than would be expected from any natural process. Its bandwidth was approximately 2 Hz, narrow enough to indicate coherent emission, but wide enough to suggest either intentional modulation or slight frequency drift. But here was the critical detail, the observation that would generate intense debate and careful scrutiny over the following weeks. The signal appeared only when the telescope was pointed at 3I Atlas, and it disappeared when the telescope was moved to observe a reference position in a nearby empty patch of sky. This on-off pattern was repeated 3 times during the observation period, with the signal appearing each time the telescope returned to tracking the object and vanishing each time it moved away. This was exactly the kind of behavior that SETI protocols were designed to confirm. A signal associated with a specific position on the sky, reproducible across multiple observations, and absent from control observations, met the basic criteria for a genuine detection, rather than an artifact of the instrument or interference from terrestrial sources. But extraordinary claims require extraordinary evidence, and the Breakthrough Listen team spent the next 72 hours running every verification test in their protocols before saying anything publicly. They confirmed that the signal wasn't present in observations of other objects at similar elevations and azimuths, ruling out a fixed, ground-based transmitter bleeding into the telescope. They verified that the frequency didn't match any known satellite communication bands, any radar systems, any aviation transponders. They checked and rechecked the data reduction pipeline, ensuring no software bugs could be creating false signals from noise. They searched historical archives for any similar signals at that frequency and found none. And critically, they attempted to redetect the signal during subsequent observations on April 9th and 10th. The signal did not repeat. In the careful world of radio astronomy, a non-repeating signal occupies an uncomfortable category. It's too interesting to dismiss, but insufficient to claim as a definitive detection. The history of SETI is populated with intriguing non-repeating signals. The famous WOW signal, detected at Ohio State in 1977. Various transient candidates from the Allen Telescope Array and Parkes Observatory. None ever confirmed, none providing the repeatable evidence that would transform them from curiosities into discoveries. The Breakthrough Listen team published their results in an astronomer's telegram, a platform for rapid dissemination of time-sensitive observational data. Their abstract was cautious. We report the detection of a narrow-band radio signal at 1.42 GHz is associated with the interstellar object 3I Atlas during observations conducted on April 7. The signal met initial criteria for a technosignature candidate, but was not detected in subsequent observations. Further monitoring is required to determine if the emission is reproducible. That word, technosignature, appearing in an official scientific publication in connection with a specific observed object, triggered another surge of media attention. But now the coverage carried a different tone. The initial reports about spectroscopic anomalies could be explained away as interesting puzzles that would probably yield to natural explanations once better data arrived. Thermal irregularities and geometric radar echoes might suggest unusual structures, but didn't necessarily imply technology. A narrow-band radio signal at the hydrogen line, appearing only when pointed at the object, was harder to contextualize as natural. It walked up to the line, separating unexplained phenomena from deliberate transmissions. And while it didn't quite cross that line, a single non-repeating detection never does, it stood close enough to make people who had been comfortable with ambiguity begin to feel genuinely unsettled. Dr. Loeb published an article in Scientific American titled "The Case for Taking 3I Atlas Seriously as a Technological Artifact." In it, he synthesized the accumulated evidence. The emission peaks at unknown wavelengths, the thermal uniformity and excess heat, the rotational stability and galactic alignment, the geometric radar echoes, and now the radio candidate signal. He presented the Bayesian argument. Given a set of observations, what is the relative probability of hypothesis H1, natural origin, versus hypothesis H2, technological origin? Bayesian reasoning requires assigning prior probabilities to each hypothesis and then updating those probabilities based on the evidence. Loeb argued that while the prior probability of technological origin should indeed be low, there's no a priori reason to expect any particular interstellar object to be artificial. The accumulation of anomalies, each individually improbable under natural hypotheses, shifted the posterior probability significantly. He didn't claim certainty. He didn't claim proof. He claimed that the data warranted serious consideration of technological origin as a competitive hypothesis alongside natural ones, and that scientific integrity required investigating both possibilities with equal rigor rather than defaulting to natural explanations because they felt more comfortable. The article generated predictable responses. Some colleagues supported his approach, noting that science advances by entertaining unconventional ideas when conventional ones struggle to explain observations. Others criticized what they saw as premature speculation, arguing that the absence of natural explanations for certain features didn't automatically validate technological ones. That we don't know yet was a perfectly acceptable scientific position, and that jumping to artifact hypotheses risked damaging astronomy's credibility. But beneath the public debate, a different conversation was occurring within government circles. The combination of unusual physical characteristics and a possible radio transmission from an interstellar object had triggered protocols that extended beyond scientific curiosity into domains of national security and strategic planning. If there existed even a small probability that 3I Atlas was an artifact of non-human intelligence, that probability carried implications that needed to be evaluated by people whose job was to consider low-probability, high-impact scenarios. In late April, a working group was convened under the auspices of the National Security Council, bringing together astronomers, physicists, military analysts, intelligence professionals, and policy advisors. The meetings were classified, but their existence was not entirely secret enough people were involved that word inevitably leaked. The group's mandate was to assess the evidence surrounding 3I Atlas, evaluate the range of possible explanations, and recommend what actions, if any, the United States government should take in response to the object's presence in the solar system. The working group received briefings on all available data. They reviewed the spectroscopic observations, the thermal analyses, the trajectory studies, the radar echoes, and the radio detection. They heard from skeptics who argued that each anomaly, while interesting, could potentially be explained by natural processes we simply hadn't yet identified, and that the convergence of multiple anomalies might reflect gaps in our understanding rather than evidence of design. They heard from those less skeptical who walked through the probability calculations and argued that at some point, the accumulation of individually unlikely features should shift our assessment from probably natural but weird to possibly artificial, and we should find out. One presentation, delivered by a physicist from Lawrence Livermore National Laboratory, focused on the energetics of interstellar travel. If 3I Atlas was indeed an artifact, it had crossed at least 40 light-years of space, and likely much more if its journey had begun longer ago than its most recent stellar encounter. At its current velocity of 42 kilometers per second, it would take nearly 30,000 years to cross a single light-year. This meant that if it was a probe, it was either extraordinarily patient, representing a civilization that thought in timescales of tens or hundreds of thousands of years, or it had decelerated from a much higher velocity upon entering the solar system. The latter possibility introduced additional questions. Deceleration requires energy. To slow down from, say, 10% of light speed, a velocity that would make interstellar travel more feasible on timescales relevant to technological civilizations. To 3I Atlas's current velocity would require expending kinetic energy equal to about half the original kinetic energy, which for even a modestly sized object would be enormous. Where had that energy gone? If into heat, the object should have a thermal history visible in its spectral characteristics, signs of surface modification from extreme temperatures. If into expelled propellant, there should be signatures of that mass ejection, changes in trajectory, residual gases. The observations showed none of these features. Unless, the physicist suggested, the deceleration had occurred long ago, perhaps decades or centuries before the object entered the inner solar system, at a distance where no human instruments were watching. Or unless the deceleration mechanism was something more exotic, some method of shedding velocity that didn't involve conventional propellant or thermal signatures. He didn't elaborate on what such mechanisms might be, but the implication was clear. If we were dealing with technology capable of crossing interstellar space, we shouldn't assume we understood the engineering principles involved. Another briefing examined historical precedents, the occasions when unusual astronomical observations had generated speculation about artificial origins before natural explanations were found. The pulsar discovery in 1967, initially labeled LGM-14 Little Green Men because of the radio pulse's astonishing regularity, until the astrophysics of rotating neutron stars became clear. The WOW signal of 1,977, still unexplained but generally considered more likely to be a rare natural phenomenon or terrestrial interference than an extraterrestrial broadcast. The Tabby star, KIC 8462852, whose irregular dimming pattern had sparked suggestions of alien megastructures before more prosaic explanations involving dust clouds gained favor. The history suggested caution, a reminder that nature's repertoire of phenomena exceeds human imagination, that the universe regularly produces things we didn't predict and don't immediately understand. But the briefing also noted a crucial difference between those historical cases and 3I Atlas. All of those previous anomalies involved distant phenomena that remained distant, objects or signals we could observe but not reach, not touch, not study up close. 3I Atlas was in our solar system. It was accessible, at least in principle. If we wanted to know what it was made of, we could send a spacecraft to find out. That changed the equation from pure speculation to actionable intelligence. This thought that we could actually investigate the object directly rather than merely observing it from afar led to the working group's primary recommendation. that NASA should immediately begin planning a rapid deployment mission to intercept 3I Atlas and conduct close-range observations, possibly including a landing or sample return if feasible. Such a mission would be unprecedented in its speed of development and launch. Typical deep space missions require years of planning, engineering, and testing. But the working group argued that the unique circumstances, the potential significance of the target, combined with its limited availability before it exited the solar system, justified accelerated timelines and accepting higher risk than normal. The recommendation went to the NASA administrator, who faced a complex decision. Authorizing a rapid deployment mission to an interstellar object based on ambiguous evidence would require significant resources, would draw intense public scrutiny, and would inevitably be seen as either visionary or reckless, depending on what the mission found. If 3I Atlas turned out to be an unusual but natural object, the mission might still produce valuable science, but would be viewed as an overreaction. If it turned out to be artificial, and the United States had taken the initiative to investigate, that would be one kind of historical legacy. If it was artificial and we had done nothing while it passed through our cosmic neighborhood, that would be another kind of legacy entirely. In May, NASA announced that it was conducting a feasibility study for a mission to 3I Atlas, describing it as an opportunity to investigate an interstellar visitor with unique properties. The announcement was careful not to emphasize the more speculative aspects of the object's characteristics, focusing instead on the scientific value of studying any interstellar object up close, the rarity of such opportunities, and the possibility that 3I Atlas might provide insights into planetary formation processes in other stellar systems. But the astronomy community understood what the announcement implied. Feasibility studies for missions to specific targets don't get initiated without strong scientific or strategic motivation. The fact that NASA was considering a rapid deployment mission meant that at least some decision-makers believed the situation warranted urgency, and the most likely source of that urgency was the possibility, however uncertain, that 3I Atlas represented something more than a wandering rock. While the mission study proceeded through its initial phases, observations of the object continued with increasing intensity. Every major observatory capable of seeing 3I Atlas devoted time to it, creating the most comprehensive dataset ever assembled for a single small body. The Hubble Space Telescope obtained high-resolution visible light images, revealing that the object was elongated with an approximate axis ratio of 4:1, similar to Oumuamua, but with a smoother outline, lacking the obvious fragmentation that had characterized its predecessor. The James Webb Space Telescope continued its infrared spectroscopy, searching for additional emission features and refining the measurements of the known peaks. Ground-based facilities contributed optical light curves, radar observations, and attempted radio monitoring. From this accumulated data, a more detailed picture of 3I Atlas emerged, though this picture raised as many questions as it answered. The object's size was estimated at approximately 400 meters along its long axis and 100 meters across its short axis, giving it a shape roughly similar to a cylinder or prolate spheroid. Its surface was dark, with an albedo around 0.04, comparable to carbonaceous asteroids but slightly more reflective in certain wavelengths. The spectroscopic data confirmed the presence of carbon-based compounds on the surface, along with what appeared to be hydrated minerals, suggesting the object had been exposed to water at some point in its history. But the geometric regularity hinted at by the radar echoes became more apparent in the visible light images. Hubble's highest resolution observations, obtained when the object was near its closest approach to Earth at 2.1 AU, showed surface features that appeared linear, running parallel to the long axis. These features were subtle, at the limit of the telescope's resolution, but they suggested ridges or grooves, with spacing on the order of tens of meters. Whether these represented natural fractures from ancient impacts, tectonic features from thermal stresses, or something else entirely remained ambiguous from the imaging data alone. The emission peaks continued to pulse with each rotation, unchanging in wavelength, unchanging in their intensity ratios, unchanging in their rotational modulation. Attempts to identify natural substances that could produce these wavelengths through any combination of fluorescence, phosphorescence, or other photoluminescent processes had failed. The wavelengths simply didn't match anything in the known spectroscopic libraries. This left several possibilities. Either the emission came from materials with compositions that didn't exist in our solar system, formed under conditions not found around our sun, or the emission was being generated by devices designed to produce light at those specific frequencies. Dr. Chen, who had made the original discovery of the emission peaks, spent months exploring the first possibility, consulting with mineralogists and geochemists about exotic materials that might form in interstellar environments, carbon-based compounds exposed to cosmic rays in extreme cold, metallic glasses formed in supernova ejecta, crystalline structures that don't exist in terrestrial geology because Earth's formation environment lacked certain elements or conditions. She compiled lists of hypothetical substances, calculated their theoretical spectroscopic properties, and compared them to the observations. None matched. Some came close in one wavelength region but failed in others. Some matched the emission behavior but predicted additional features that weren't observed. It was like trying to solve a jigsaw puzzle where none of the pieces quite fit, where each arrangement left gaps that couldn't be closed. In June, a paper appeared on RxIV, the preprint server where astronomers share results before peer review. The authors were a collaboration of spectroscopists from 5 institutions, and their title was direct: Coherent Narrowband Emission from 3I Atlas, Constraints on Natural Mechanisms. The paper systematically evaluated every proposed natural explanation for the emission peaks, from exotic mineralogy to novel chemical reactions to quantum mechanical processes in unusual atomic configurations. For each mechanism, they derived the physical conditions required to produce emission at the observed wavelengths, calculated the expected emission line widths and intensity ratios, and compared these predictions to the data. Their conclusion was carefully worded but unambiguous. We find no known natural mechanism that can simultaneously explain the observed wavelengths, line widths, intensity ratios, and rotational modulation of the 3 emission features detected from 3I Atlas. While we cannot exclude the possibility of unknown natural processes, the properties of these emissions are consistent with coherent artificial sources, such as laser diodes or other narrowband emitting devices. The word laser in connection with 3I Atlas was new, and it carried specific implications. Lasers produce coherent light through stimulated emission, a quantum mechanical process that requires a gain medium, a pump energy source, and a resonant cavity. Nature can produce coherent emission through astrophysical masers, but these operate in specific molecular transitions under specific conditions, and they don't explain the wavelengths observed from 3I Atlas. To produce laser emission at arbitrary wavelengths requires engineering, requires selecting appropriate gain media, and designing systems that can maintain the population inversion necessary for stimulated emission. It requires technology. The paper didn't claim that 3I Atlas definitely contained lasers. It claimed that laser emission was consistent with the observations in ways that natural processes were not, and that this warranted consideration. But the scientific community understood what this meant. If the emission peaks were indeed from artificial coherent light sources, then the object wasn't just artificial in the sense of being manufactured, it was active, it was powered, it was operating. This raised immediate questions about the energy source. Lasers require power. Even low-power laser diodes need milliwatts to watts. 3 lasers operating continuously for the months that 3I Atlas had been under observation would require a sustained power supply. The most obvious source would be solar panels, converting sunlight into electricity. But the object's distance from the sun meant that solar flux was a tiny fraction of what it is near Earth. At 3I Atlas's current distance of approximately 10 AU, solar intensity was 1% of Earth's level. At its furthest observed distance of 12 AU, it was less than 0.7%. To generate even modest power from solar cells at that distance would require large arrays, and the object showed no obvious sign of extended solar panels in the Hubble images. Alternative power sources included radioisotope thermoelectric generators, the same technology used in deep space probes like Voyager and New Horizons, which convert heat from radioactive decay into electricity. A sufficiently large RTG could power laser diodes for decades or centuries. But RTGs produce heat as a byproduct, and while 3I Atlas did show slight thermal excess, the magnitude was lower than expected for RTGs powerful enough to run multiple lasers continuously. Unless the thermal management was extremely efficient, channeling waste heat into an internal heat sink or radiating it preferentially in directions not observed from Earth. A third possibility, more speculative, was that the object possessed some form of energy storage that had been charged long ago, perhaps when it was closer to its parent star, and was now slowly depleting its reserves. Capacitors, batteries, or more exotic storage mechanisms could in principle hold enough energy to run low-power systems for extended periods. But maintaining charge over interstellar timescales presented significant challenges, as even the best electrical storage systems experience self-discharge. Or perhaps the power source was something we didn't recognize, some technology that didn't fit our categories. This was the uncomfortable implication of the artifact hypothesis. If we were dealing with engineering from a civilization that had mastered interstellar travel, we shouldn't expect to understand all aspects of their systems, any more than a person from the Bronze Age would understand a lithium-ion battery or a photovoltaic cell. In July, the Breakthrough Listen team announced that they would be conducting a second, more extensive radio observation campaign targeting 3I Atlas. This time, they would use the Meerkat Array in South Africa in addition to the Green Bank Telescope, providing two widely separated observing sites to help distinguish genuine signals from local interference. They would cover a broader frequency range, from 100 MHz to 20 GHz, and would employ advanced signal processing algorithms designed to detect not just narrowband carriers but also pulse signals, frequency-modulated transmissions, and other patterns that might indicate communication or telemetry. The observations were scheduled to span 2 weeks in August, covering multiple rotations of the object and multiple times of day to account for any temporal patterns in potential transmissions. The team emphasized that they were not assuming the object was artificial, merely that its anomalous characteristics justified thorough investigation using the most sensitive search techniques available. The August observations began on the 5th and immediately produced interesting data, though not in the way the team had expected. Instead of detecting narrowband signals similar to the April candidate, they observed something more subtle, a low-frequency modulation in the object's overall radio brightness. This wasn't a discrete signal at a specific frequency, but rather a variation in the continuum emission, a gentle rise and fall in the radio flux across a broad range of frequencies. The modulation had a period of 19.2 seconds, exactly matching the temporal structure seen in the radar, echoes from the Arecibo data. And it was phase-locked with the object's rotation, repeating 12 times per rotation period just as the radar features had. This suggested that whatever surface structures were creating the radar reflectivity pattern were also affecting the object's passive radio emission, its natural tendency to emit thermal radiation at radio wavelengths. Dr. Santos, reviewing the new data alongside her original radar analysis, recognized the pattern immediately. The 19.2-second period divided the 4.73-hour rotation period into exactly 887 cycles. This wasn't an approximate match, it was precise to within the measurement uncertainty. Such precise integer ratios don't typically arise by chance. They suggest coupling, resonance, some physical relationship between the processes that sets them to simple fractional values. She ran calculations exploring what kind of surface structure could produce both the radar echo pattern and the radio emission modulation. The geometry had to be regular, repeating around the object's circumference with a spatial frequency that produced 12 reflections or emission features per rotation. If the object was roughly cylindrical with a length of 400 meters, and these features were distributed around its circumference of approximately 315 meters, assuming a diameter of 100 meters, then 12 features meant spacing of roughly 26 meters. This matched the scale of the linear features visible in the Hubble images. The ridges or grooves that ran along the object's length, subtle but detectable at the telescope's resolution limit, appeared to be spaced at intervals consistent with what the radio and radar data required. Everything was pointing to the same conclusion. 3I Atlas possessed regular geometric structures at a scale of tens of meters, arranged with rotational symmetry around its long axis, and these structures affected how the object interacted with electromagnetic radiation across multiple wavelengths. Natural processes can create regular patterns. Hexagonal basalt columns form as cooling lava contracts, creating stress patterns that organize into geometric arrays. Sand dunes on Mars form with surprising regularity, spaced by wind patterns and particle dynamics. The rings of Saturn show structures shaped by orbital resonances with moons. Nature is full of order emerging from physical laws, but the structures on 3I Atlas were regular across multiple independent characteristics. Their spacing, their radar reflectivity, their radio emission properties, their alignment with the rotation axis. Each of these characteristics could potentially be explained naturally in isolation. Together, they formed a pattern that was harder to reconcile with random formation. It was like finding stones arranged in a circle. Any individual stone could have gotten there by chance, but the arrangement suggests intention. Dr. Loeb, in a blog post analyzing the new radio data, made an analogy to architecture. When we find a building with windows spaced at regular intervals, walls meeting at right angles, and a roof aligned parallel to the ground, we don't assume these features arose independently through separate geological processes. We recognize that they're all consequences of a single fact. Someone designed the building with those regularities because they serve functional purposes. The question with 3I Atlas is whether we're looking at something similar, multiple regularities that are all downstream of a design process, or whether we're being fooled by coincidence and incomplete understanding. The analogy was imperfect, and critics were quick to point out its weaknesses. Buildings don't form naturally, but natural objects with multiple regularities do exist. Critics argued that cherry-picking unusual features and asking, "What are the odds?" while ignoring the billions of objects in the galaxy that don't show these features, was a classic statistical fallacy. We notice the unusual, precisely because it's unusual. But unusual things must exist somewhere. This debate, whether the accumulation of anomalies constituted genuine evidence of artificiality or merely reflected the human tendency to see patterns and significance where none existed, became the central axis around which discussions of 3I Atlas revolved throughout the summer and fall of 2025. It was a debate without obvious resolution because it turned on questions about how to weigh evidence in the face of profound uncertainty, how much skepticism was appropriate versus how much was excessive, and ultimately, what standards of proof should be required before entertaining seriously the hypothesis that we had detected a probe from another civilization. But while this philosophical debate played out in journals and conferences and social media, the practical work of trying to understand 3I Atlas continued. NASA's feasibility study for a rapid deployment mission progressed to Phase 2, which involved selecting specific mission architectures and evaluating whether existing launch vehicles and spacecraft buses could be adapted to reach the object within the available time window. The trajectory calculations were challenging. 3I Atlas was moving outward from the Sun at 42 kilometers per second on a hyperbolic escape trajectory. Any spacecraft sent to intercept it would need to match not just its position but also its velocity, requiring enormous amounts of propellant. The most feasible approach was a fast flyby, where the spacecraft would accelerate outward from Earth, possibly using a Jupiter gravity assist to boost velocity, and then catch up to the object for a brief encounter at high relative velocity. Such a flyby would be brief, perhaps a few hours within the object's vicinity, with closest approach lasting seconds to minutes. But during that time, the spacecraft could obtain high-resolution images showing details down to centimeter scales, could conduct spectroscopy, revealing surface composition with far greater precision than possible from Earth, could measure magnetic fields if any existed, could detect any outgassing or particle emission, and could possibly even deploy small sub-satellites or penetrators that would impact the surface while the main spacecraft flew past. The mission designers at the Jet Propulsion Laboratory worked through multiple scenarios, optimizing trajectories and payload configurations. The fastest feasible mission profile, using a near-term launch window in early 2026 and a Jupiter gravity assist, could reach 3I Atlas in mid-2027, when the object would be at approximately 18 AU from the Sun. This was before it became too distant for reliable communication, and while there was still sufficient sunlight for solar-powered spacecraft systems, the mission would cost approximately $800 million in NASA's preliminary estimates, expensive for a rapid deployment mission, but modest compared to flagship-class missions like Europa Clipper or Mars Sample Return. The question wasn't whether the mission was technically feasible. The question was whether the scientific and strategic justification was sufficient to commit the resources and accept the risks. In September, another development added urgency to this question. The European Space Agency's Gaia mission, which had been mapping the positions and motions of over 1 billion stars with unprecedented precision, released updated data that included refined measurements of 3I Atlas's trajectory. The new data allowed for better reconstruction of the object's path through space over longer timescales, tracing its motion backward to determine more precisely where it had come from. Dr. Talbot at JPL incorporated the new astrometry into his trajectory models and ran extended simulations. The results refined his earlier estimates, but also revealed something new. Approximately 50,000 years ago, 3I Atlas had passed within 2 light-years of a star system designated HD 28343, a K-type orange dwarf located 44 light-years from Earth in the constellation Perseus. The close encounter wasn't close enough to have significantly perturbed the object's trajectory. 2 light-years is still vast, but it was close enough to be potentially significant if 3I Atlas had been traveling through that region deliberately. HD 28343 was unremarkable by most astronomical standards. It had about 80% the mass of the Sun, shone with roughly 40% the luminosity, and had an estimated age of around 8 billion years, old enough for planetary systems to have formed and for life, if it had arisen, to have evolved. Surveys had detected no known exoplanets around the star, but most exoplanet detection methods are biased toward large planets in close orbits, and the absence of detected planets didn't mean the star lacked them. What made HD 28343 interesting in the context of 3I Atlas was that the object's velocity vector, when traced backward, pointed almost directly toward the star, not exactly, but within the uncertainties of the trajectory reconstruction. If you launched an object from the HD 28343 system 50,000 years ago and aimed it toward our solar system, and if that object traveled at the velocity 3I Atlas currently possessed, it would arrive at approximately the time and place where 3I Atlas was first detected. This didn't prove anything. Space is mostly empty, and trajectories can point at stars by coincidence, but it provided something that had been missing from previous analyses, a specific origin hypothesis that could be tested. If 3I Atlas had been sent from HD 28343, either deliberately or as an artifact ejected from that system by natural processes, then we could make predictions. We could examine that star system for unusual characteristics, search for signs of technology or activity, look for other objects on similar trajectories that might represent a fleet or swarm. The Breakthrough Listen initiative immediately redirected some of its observing resources toward HD 28343, conducting deep radio searches for technosignatures, narrowband carriers, Unusual emission patterns? Anything that might indicate the presence of technology in that system. SETI searches had observed thousands of nearby stars over the decades, but HD 28343 had never been a priority target. It wasn't particularly close, wasn't particularly sun-like, and hadn't shown any unusual characteristics in previous observations. Now, suddenly, it became one of the most interesting targets in the sky. The radio searches found nothing. No signals, no anomalies, just the normal background of stellar radiation and cosmic noise. But this wasn't particularly surprising or discouraging. Even if HD 28343 hosted a technological civilization, there was no reason to expect we'd detect their transmissions unless they were deliberately beaming signals toward us. And if they had sent a probe to our solar system 50,000 years ago, they wouldn't necessarily still be transmitting radio signals that we could detect across 44 light-years. Still, the connection to a specific star system made 3I Atlas feel more real, more concrete. It transformed the object from an abstract mystery to something with a possible address, a possible origin story. It made it easier to imagine the scenario where, 50,000 years ago, some civilization around an orange star in Perseus had decided to explore the galaxy and had launched automated probes toward nearby stellar systems, including ours. Those probes would have been traveling through space, while Homo sapiens was still sharing Earth with Neanderthals, while the last ice age was reaching its peak, while no human had yet invented agriculture or writing or civilization. And one of those probes, if that's what it was now approaching the outer regions of our solar system, still functioning after millennia in the void, still transmitting its narrow-band emissions, still rotating with perfect regularity, still carrying whatever instruments or cargo or information it had been launched with all those thousands of years ago. This narrative, speculative but no longer entirely implausible, changed the tenor of discussions about the NASA mission. The question shifted from, should we investigate this weird object? To, can we afford not to investigate this potential probe from another civilization? The political and public relations calculus changed. A mission that might have seemed like an expensive gamble on a long shot became reframed as a unique opportunity to make first contact with extraterrestrial technology, an opportunity that would pass if we didn't act quickly. In October, NASA Administrator William Nelson announced at a press conference that the agency would proceed with mission planning for what was now officially designated the Interstellar Object Reconnaissance Mission, or IORM. The mission would use a modified version of the New Horizons spacecraft bus, which had proven capable of rapid transit to the outer solar system during its Pluto flyby. The payload would include high-resolution cameras, infrared and ultraviolet spectrometers, a radar system, magnetometers, and a laser altimeter for precise shape and rotation measurements. If the spacecraft detected any radio emissions during its approach, it would carry a simple communication system capable of transmitting basic mathematical sequences, attempts at a first message, just in case there was anyone or anything listening. The announcement generated immediate international attention. Other space agencies, ESA, Roscosmos, JAXA, the Chinese National Space Administration, issued statements expressing interest in contributing to or coordinating with the NASA mission. The United Nations Office for Outer Space Affairs convened an emergency session to discuss protocols for investigating potential extraterrestrial artifacts, though no formal international agreement existed for such situations. The conversation quickly became entangled in questions of jurisdiction, information sharing, and who would control the data if the mission succeeded. But these diplomatic complications were problems for the future. In the immediate term, the mission team at JPL had less than a year to finalize the spacecraft design, integrate the payload, test all systems, and be ready for the launch window in February 2026. This was an extraordinarily compressed timeline by normal standards, but the team was staffed with veterans of previous rapid deployment missions, people who understood how to make hard trade-offs and accept calculated risks. While the engineering work proceeded, the observational campaign continued. Every rotation of 3I Atlas was monitored by at least one major telescope, building a continuous record of its behavior over months. This extensive baseline allowed astronomers to search for any changes or evolution in the object's characteristics. Were the emission peaks stable over time, or did they show any variation? Was the thermal excess constant, or did it decline as the object moved further from the Sun? Was the rotation period truly constant, or were there subtle accelerations or decelerations that might indicate outgassing or other active processes? The answer, to the frustration of those hoping for additional clues, was that 3I Atlas remained remarkably constant. The emission peaks held their wavelengths and intensity ratios to within the measurement precision. The thermal profile remained stable. The rotation period showed no detectable change. The object was, in every observable way, unchanging. It continued doing exactly what it had been doing since its discovery, as if following some predetermined program, as if it were a machine executing instructions with indifference to human curiosity. This constancy was itself informative. Natural objects change. Comets outgas, creating asymmetric forces that alter their spins. Asteroids shed dust and tiny fragments. Thermal cycling creates stresses that crack surfaces. The fact that 3I Atlas showed none of these behaviors suggested either that it was inactive in ways that natural bodies typically aren't, or that it possessed some mechanism for maintaining stability despite the perturbations that should naturally affect it. In November, a team of researchers from MIT published a detailed analysis of what the object's stability implied about its internal structure. They modeled 3I Atlas as a solid body and calculated how its rotation should evolve over time due to various effects: thermal radiation pressure, solar wind drag, interstellar gas friction, the slight gravitational tugs from distant planets. Then, they compared these predictions to the observed constant rotation period. Their conclusion was that for 3I Atlas to maintain such rotational stability, it had to possess a very specific mass distribution. Either it was almost perfectly uniform in density, like a solid metal cylinder, or it was actively controlled, with internal mass shifted by motors or flywheels to compensate for external perturbations. The former possibility required the object to be made of materials and formed through processes that were unusual but potentially natural. The latter required technology, specifically technology for attitude control of the kind used in artificial satellites. The paper didn't claim to have definitively proven either scenario. It simply laid out the constraints. If 3I Atlas is natural, it must have properties X, Y, and Z. If it's artificial, it must have capabilities A, B, and C. Either way, we're looking at something unusual. Either way, we need to get closer and look more carefully. As 2025 drew toward its close, the scientific community found itself in an unusual position. There existed an object in the solar system that showed multiple characteristics inconsistent with typical natural bodies, and a mission was being prepared to investigate it directly. But the mission wouldn't reach its target for another year and a half, and in the meantime, the object continued its journey outward, becoming gradually fainter and harder to observe as distance increased. This waiting period created a strange tension. Evidence continued to accumulate, each new observation adding detail to the portrait of 3I Atlas, but none of the observations definitively resolved the central question of the object's nature. The artifact hypothesis remained exactly that, a hypothesis competitive with natural explanations but not proven. The object remained enigmatic, neither clearly natural nor clearly artificial, occupying an uncomfortable middle ground that resisted easy categorization. Dr. Chen, interviewed by Nature magazine in December, reflected on the experience of living with this uncertainty. As scientists, we're trained to be comfortable with not knowing, she said. We work with incomplete data all the time. We formulate hypotheses and test them and revise them. But this is different. This isn't about understanding some abstract phenomenon. If 3I Atlas is artificial, it means we're not alone. It means someone else built something and sent it through space, and it's here now, in our solar system. That's not just a scientific question. It's a philosophical one, maybe even an existential one, and we won't know the answer until the spacecraft gets there. The article captured something of the mood that had settled over the researchers most deeply involved with 3I Atlas. There was excitement. Certainly, the possibility of discovering extraterrestrial technology was perhaps the most exciting prospect in the history of astronomy. But there was also a kind of existential vertigo, a sense that they were standing at a threshold between two very different universes, one where humanity was alone in the cosmos, special and unique, and one where we were merely one species among many, late arrivals to a galaxy that had been populated by others long before we evolved. The threshold wasn't crossed yet. The question remained open, but it was open in a way that felt different from previous SETI searches or speculations about alien life. Those had always been about possibilities, about maybes and somedays. This was about something real and specific and observable, something that existed whether we understood it or not, something that would still be there when the spacecraft arrived, waiting to be examined. In January 2026, as mission preparations entered their final phase, Dr. Loeb gave a lecture at Harvard titled "What We Know and What We Don't About 3I Atlas." The room was packed, with people standing along the walls and sitting in the aisles. He walked through the evidence systematically: the emission peaks, the thermal anomalies, the rotational stability, the geometric regularity, the possible connection to HD 28343. For each piece of evidence, he presented both natural and artificial interpretations, showing how the data could be viewed through different lenses. But toward the end of the lecture, he made an argument about burden of proof. In most of science, he said, extraordinary claims require extraordinary evidence, and that's appropriate. If you claim you've discovered a new fundamental force or detected faster-than-light particles, the burden is on you to rule out every possible mundane explanation. But I want to suggest that the situation with 3I Atlas is different. The extraordinary claim isn't that it's artificial. The extraordinary claim is that nature produces objects with this specific combination of characteristics. We know technology exists, we build it ourselves. We have existence proof that technological civilizations can arise because we're one. What we don't have existence proof of is natural processes that create objects with precise rotational stability, geometric surface patterns, narrowband coherent emission at arbitrary wavelengths, and trajectories aligned with galactic coordinates. So perhaps the burden of proof should be reversed. Perhaps we should be asking, if this is natural, show us the mechanism. And if no such mechanism can be demonstrated, we should seriously entertain the alternative. It was a carefully crafted rhetorical move, and it generated immediate debate. Some in the audience agreed, nodding along. Others visibly disagreed, preparing rebuttals they would deliver during the question period. But what was remarkable was that the debate was happening at all, that a serious scientific discussion at Harvard University was entertaining the possibility that an object in our solar system might be an artifact of extraterrestrial technology, and that this wasn't fringe speculation but a hypothesis being considered by mainstream scientists using standard methods of evidence evaluation. The lecture was recorded and posted online, where it accumulated millions of views within days. The comments sections and discussion forums became battlegrounds between those convinced that 3I Atlas represented first contact and those equally convinced that it was an unusual but natural object being hyped by attention-seeking scientists. Between these extremes, most people occupied a position of uncertain curiosity, waiting for more definitive evidence while allowing themselves to imagine what it would mean if the artifact hypothesis turned out to be true. As February approached, the Interstellar Object Reconnaissance Mission spacecraft completed final integration and testing at the Kennedy Space Center. The launch window opened on February 15th, and weather conditions were favorable. At 11:42 UTC, an Atlas V rocket lifted off from Launch Complex 41. carrying the spacecraft toward its rendezvous with 3I Atlas in mid-2027. The launch was broadcast live and watched by enormous audiences worldwide. There were viewing parties at universities and science museums. Social media exploded with commentary and speculation. For a few minutes, as the rocket climbed toward space, humanity collectively held its breath, united in witnessing the beginning of a journey that might answer one of our oldest questions. The spacecraft separated from its upper stage 30 minutes after launch and began its coast phase toward Jupiter, where a gravity assist in June would bend its trajectory and accelerate it toward 3I Atlas. Solar panels deployed successfully. Communication systems checked out. All instruments powered up and returned nominal data. The mission team at JPL exchanged relieved looks and cautious smiles. They had launched successfully. Now came the long wait. But even as the spacecraft began its journey, observations of 3I Atlas from Earth-based telescopes continued to yield surprises. In March, a team using the European Southern Observatory's Very Large Telescope in Chile reported detecting faint diffuse emissions surrounding the object, not a coma like a comet would produce, but a more subtle haze of scattered light that suggested the presence of small particles, perhaps micron-sized dust grains, in the object's vicinity. This was unexpected. If 3I Atlas was shedding particles, even in tiny amounts, it suggested some kind of activity, some process ejecting material from the surface or interior. But the dust production rate, if that's what it was, appeared to be extremely low orders of magnitude less than even the weakest comets, and the dust didn't show the characteristic fan or tail shape that cometary dust exhibits when pushed by solar radiation pressure. Instead, it formed a roughly spherical haze centered on the object, as if the particles were being ejected uniformly in all directions or were somehow bound to the object by weak forces. One hypothesis was that the particles represented debris from micrometeoroid impacts, the continuous rain of tiny particles that bombards all objects in space. But the density of the haze seemed higher than this mechanism should produce, especially at 3I Atlas's current distance where the micrometeoroid flux was low. Another hypothesis involved electrostatic levitation of dust, where charged particles were lifted from the surface by electromagnetic forces and held in suspension nearby. This mechanism was known to operate on the Moon and asteroids, but typically required solar-wind interactions that were much weaker at 3I Atlas's distance, or perhaps several researchers suggested with varying degrees of seriousness the particles represented exhaust from onboard systems, trace gases or particles expelled by whatever mechanisms maintained the object's functions. This interpretation was the most speculative, but also the hardest to definitively rule out. If 3I Atlas was indeed a functioning probe, it would need to manage heat, possibly cycle gases for attitude control, and might produce small amounts of waste products that would be expelled into space. The dust detection added another item to the growing list of characteristics that needed explanation. It didn't prove artificiality, but it complicated natural scenarios, requiring additional processes beyond those needed to explain the object's other properties. Each new observation seemed to deepen the mystery rather than resolve it, adding layers of complexity to an already puzzling picture. By spring 2026, a substantial fraction of the world's major observatories had contributed data to the 3I Atlas dataset. The object had become the most intensively studied small body in history, observed across the electromagnetic spectrum from radio to ultraviolet, tracked continuously for over a year, analyzed by hundreds of researchers across dozens of institutions. The accumulated data filled terabytes of storage, and specialized working groups had formed to manage different aspects of the analysis: the Emission Features Working Group, the Thermal Properties Group, the Trajectory and Rotation Group, the Surface Morphology Group, the Radio Emissions Group. These working groups met regularly via teleconference, sharing results and coordinating observations. The meetings had an unusual quality, a sense that everyone involved understood they might be participants in something historic. When they discussed spectroscopic measurements or rotational dynamics, They weren't just doing normal astronomy. They were trying to determine whether humanity was alone in the universe, whether the cosmos contained other minds and other technologies, whether our presence was unique or commonplace. Dr. Constantine, whose leaked memo had helped trigger the broader investigation, chaired many of these meetings. She had become, somewhat reluctantly, one of the public faces of the 3i Atlas research effort, giving interviews and writing popular articles explaining the scientific process and the current state of knowledge. In a long essay published in Scientific American, she addressed the question that many people were asking: why was it taking so long to reach a definitive conclusion? The difficulty, she wrote, is that we're trying to distinguish between two hypotheses that make similar predictions for most observations. An unusual natural object and a designed artifact can look very similar from a distance. They're both small, dark, roughly cylindrical bodies reflecting sunlight. The differences appear in subtle characteristics, rotational stability, surface regularity, emission properties that require extremely precise measurements to detect, and even more careful analysis to interpret. And even when we find characteristics that seem hard to explain naturally, we have to consider that our understanding of natural processes is incomplete. Nature has surprised us before. It will surprise us again. So we need to be both open-minded enough to consider artifact hypotheses seriously and skeptical enough not to accept them prematurely. She went on to discuss what the spacecraft mission would likely reveal. When IORM reaches 3i Atlas, we'll get data that will be transformative regardless of what we find. High-resolution images will show us the surface at scales of centimeters, revealing whether the geometric patterns are real or artifacts of limited resolution. Spectroscopy at close range will tell us precisely what the object is made of, whether it contains materials that don't occur naturally. Magnetic field measurements will detect any electrical systems operating inside, and if there are inscriptions or markings or interfaces on the surface, we'll see them. One way or another, the ambiguity will end. We'll know, but that knowing was still more than a year away. In the meantime, the spacecraft coasted through interplanetary space, passing Mars's orbit in April, approaching Jupiter in June. The gravity assist maneuver went perfectly, bending the trajectory and boosting velocity by an additional 8 kilometers per second. After Jupiter, the spacecraft entered its cruise phase, a long quiet period where the mission team would monitor systems, calibrate instruments, and plan the sequence of observations for the eventual encounter. As summer turned to fall in 2026, public attention on 3i Atlas waned somewhat. The initial excitement had faded without definitive resolution, and people turned to other news, other crises, other interests. But within the astronomical community, the intensity didn't decrease. If anything, it increased as researchers raced to extract every possible piece of information from Earth-based observations before the object became too faint and distant for further study. One of the last major observation campaigns occurred in October 2026, using the Atacama Large Millimeter Array in Chile. ALMA, a collection of 66 radio telescopes working together as an interferometer, had the resolution and sensitivity to detect faint emission at millimeter wavelengths that might reveal the object's temperature, distribution, and composition. The observations required multiple nights due to the object's faintness, but eventually produced detailed maps of 3i Atlas's thermal emission. The maps showed something unexpected. The thermal emission wasn't uniform around the object's circumference, despite the remarkable uniformity seen in infrared observations. There were 12 discrete warm spots, equally spaced around the rotation axis, each about 10% warmer than the surrounding surface. The warm spots' positions correlated exactly with the locations of the radar reflective features and the linear structures seen in visible light images. This correlation meant that whatever created the geometric patterns on the surface also affected the object's thermal properties. The warm spots could represent areas where internal heat was conducted to the surface more efficiently, or where surface materials had different thermal inertia, or where active heating was occurring. In any of these scenarios, The precision of the spacing and the correlation with other features strengthened the case that 3I Atlas possessed internal structure organized at large scales, not just surface features. The ALMA results would be the last major dataset obtained before the object moved beyond the reach of Earth-based observations. By November 2026, 3I Atlas had faded to magnitude 26, detectable only by the largest telescopes with long exposures, and even then barely distinguishable from background noise. It was still there, still moving outward at 42 kilometers per second, still rotating with perfect precision, still emitting its mysterious narrowband signals into space. But from Earth, it had become effectively invisible. The next time humanity would get a clear look at the object would be when the spacecraft arrived in 8 months. Those 8 months passed with agonizing slowness for the researchers most invested in the mission. The spacecraft sent back routine telemetry showing all systems healthy. Its trajectory was refined with occasional thruster firings to correct small deviations. The instruments were tested periodically to ensure they remained functional. But there was no science data. Nothing to analyze, just the slow crawl of distance markers as the spacecraft chased its target across the outer solar system. Dr. Chen spent that time working on data analysis pipelines, preparing software that could process the expected flood of information from the encounter. She wanted to be ready to extract maximum value from the brief period when the spacecraft would be close enough to gather high-quality data. She knew that the encounter would last only a few hours, and that during those hours, the spacecraft would collect more information about 3I Atlas than all the Earth-based observations combined. The thought was simultaneously thrilling and terrifying. In May 2027, the spacecraft crossed the orbit of Saturn. In June, it passed Uranus's orbital distance. By mid-July, it was approaching 3I Atlas, now at approximately 19 AU from the Sun, deep in the outer solar system, where sunlight was just a bright star and temperatures hovered barely above absolute zero. The encounter sequence began on July 18th, when the spacecraft was still 5 million kilometers from the object, but close enough to start obtaining images that showed more detail than any Earth-based telescope could. The mission team watched the first images arrive at JPL's mission control, transmitted across 6 billion kilometers of space at the speed of light, taking over 2 hours to reach Earth. The first images were disappointing not because they lacked detail, but because they showed so little. 3I Atlas was just a bright speck against the black background, barely resolved even at this distance. But over the following days, as the spacecraft closed the gap, the speck grew, features appeared, and what they revealed would change everything. By July 20th, with the spacecraft 500,000 kilometers out and closing at 15 kilometers per second relative velocity, the images showed 3I Atlas as an elongated object, clearly cylindrical, with a surface that was dark but not uniformly so. There were lighter patches, arranged in patterns. Linear features ran along its length, just as the Hubble images had hinted. But now, with resolution sufficient to see details at the 100-meter scale, those features resolved into something unmistakable. They were panels, regular rectangular sections covering most of the object's surface, each about 50 meters on a side, arranged in circumferential rings that repeated along the cylinder's length. The panels weren't perfectly aligned, some were slightly offset, some had different reflectivities, but their geometric regularity was undeniable. This wasn't rock. This wasn't ice. This was structure. The mission control room at JPL erupted in controlled chaos when these images arrived. People crowded around monitors, pointing, discussing, calculating. The mission director called for attention and established procedures for documenting and distributing the images. But everyone in that room understood what they were seeing. After months of ambiguity and debate, after careful hedging and qualified statements, they were looking at something that was very clearly not natural. Dr. Chen, watching from her office at Caltech via video link, felt tears on her face and didn't bother wiping them away. She had spent over a year analyzing spectral data, arguing with colleagues about natural versus artificial explanations. maintaining scientific skepticism even as evidence accumulated. Now, seeing those panels, that geometry, that regularity, the skepticism evaporated. We were not alone. We had never been alone. And the proof was right there, captured by cameras billions of kilometers away, in the form of a cylinder covered in regular panels tumbling through our solar system. The spacecraft continued its approach, taking images every few minutes, each one revealing more detail. By July 21st, individual panels were clearly visible, showing seams between them, showing slight variations in color and reflectivity. Some panels appeared damaged or degraded, with rough edges suggesting impacts from micrometeorites over long timescales. Others appeared pristine, their surfaces smooth and uniform. As the spacecraft closed to within 100,000 kilometers, a new feature became apparent. At both ends of the cylinder, there were structures that differed from the panels. These regions appeared more complex, with protrusions and recesses, with components that might have been antennas or sensors, or mechanisms of unknown purpose. The structure at one end, designated the forward end based on the direction of the object's motion through space, included what looked like 4 symmetrically arranged appendages, each perhaps 20 meters long, extending outward from the cylinder's central axis. The mission scientists worked frantically to adjust observation plans, ensuring the spacecraft would image these structures from multiple angles and with all available instruments. The spectrometers were programmed to focus on specific panels, looking for composition differences. The magnetometer was watching for any signs of magnetic fields that would indicate electrical systems. The radar system was active, sending pulses toward the object and measuring the characteristics of the return echo. On July 22nd, with less than 24 hours until closest approach, the spacecraft was close enough that its visible light cameras could resolve features at the 1-meter scale. The images showed that the panels weren't smooth after all. Each one had a fine texture, a pattern of squares within squares, structure at multiple scales. And near the center of each panel was a small circular feature, perhaps a meter across, that might have been a port or aperture or attachment point. The appendages at the forward end resolved into more complex shapes, revealing what looked like joints or articulation points, suggesting they might once have been movable. Whether they still functioned after 50,000 years in space was impossible to know without closer examination, but their articulated structure suggested they had served some purpose that required positioning or orientation. And then, at 14:37 UTC on July 22nd, when the spacecraft was just 10,000 kilometers from 3I Atlas and closing rapidly, the narrow-band emissions that had been detected intermittently by Earth-based radio telescopes suddenly increased in intensity. The spacecraft's radio receivers, covering a wide frequency range, detected strong emission at one point for 2 gigahertzes, the hydrogen line frequency where the April 2025 signal had appeared, along with emission at several other frequencies, including the 3 infrared wavelengths that the optical times. Spectrometers had been monitoring since the object's discovery. The signals weren't modulated with information, at least not in any way the analysis software could recognize. They appeared to be carriers, pure tones at specific frequencies, but their intensity was much higher than what had been seen from Earth. At this close range, with no atmospheric or ionospheric distortion, the signals were crisp and clear, and undeniably artificial in their characteristics. The mission team made a decision. They activated the spacecraft's communication system and transmitted a simple sequence. The first 100 prime numbers, represented as pulses in a carrier frequency, carefully chosen to avoid any frequency where 3I Atlas was transmitting. This was humanity's first deliberate attempt to communicate with an artifact of extraterrestrial technology, and the message was the mathematical equivalent of, "Hello, we are intelligent beings who understand number theory." For 3 minutes, the spacecraft transmitted its sequence while simultaneously monitoring 3I Atlas for any response. Nothing changed. The narrowband emissions continued at their steady intensities, showing no variation, no acknowledgement. The object continued its rotation, completed precisely, indifferently. If there was any intelligence there, any system capable of receiving and interpreting the spacecraft's transmission, it gave no sign. But as the spacecraft swept past at closest approach at 1922 UTC, passing within 2,500 kilometers of 3I Atlas at a relative velocity of 15 kilometers per second, every instrument gathered data at maximum rate. The cameras took hundreds of images from multiple angles. The spectrometers recorded detailed composition information from different regions of the surface. The radar system mapped the surface topography with resolution sufficient to see features the size of dining room tables. The magnetometer detected weak magnetic fields consistent with current-carrying conductors, confirming the presence of active electrical systems. And in those brief minutes of closest approach, the spacecraft's cameras captured what would become the most analyzed and discussed images in the history of space exploration. High-resolution photographs showing details down to the centimeter scale, revealing the surface of a structure built by non-human intelligence. The panels were clearly manufactured, each one precisely cut and fitted, made from what spectroscopy suggested was a metal alloy with compositions that didn't match any asteroid or meteorite known from our solar system. The joints between panels showed deliberate engineering, with overlapping edges and what might have been fasteners or clips holding them in place. Some panels had markings, not random weathering, but arranged patterns of lines and shapes that could have been labels, identifiers, assembly instructions, or something else entirely. One image showed a particularly intact section near the aft end of the cylinder, where panels met at corners with precise 90-degree angles, their edges aligned to within millimeters across spans of tens of meters. Nature doesn't build like this. Natural processes don't produce right angles, don't maintain parallelism, don't create surfaces flat and smooth across large scales. This was engineering, and seeing it in such detail left no room for doubt. As the spacecraft raced away from 3I Atlas, having spent just a few hours in proximity after traveling for 17 months across the solar system, it continued transmitting its data back to Earth. The transmission would take over 2.5 hours to arrive, traveling at light speed across the vast distance. At JPL, at NASA headquarters, at observatories and universities and space agencies worldwide, people waited for those signals, knowing that what they revealed would reshape humanity's understanding of its place in the cosmos. When the highest resolution images finally arrived and were displayed on screens in mission control, there was silence. No cheering, no celebration, just a profound collective silence as everyone present absorbed what they were seeing. These weren't just images of an unusual object. They were images of an artifact. A probe, a vessel of some kind, built by a civilization that had existed around a distant star, built with purposes we could only guess at, built with technologies we were only beginning to understand, built and launched into the vast, empty dark to travel for tens of thousands of years until it reached our solar system and passed through, still transmitting, still functioning, still pursuing whatever mission had been programmed into its ancient systems. Dr. Chen was in that room when the images arrived, having flown to JPL to witness the encountered data in person. She stared at the screen, showing a close-up of those panels, those seams, those precise geometries, and felt a sensation she would later struggle to describe. It wasn't quite vindication, though her analysis of the emission spectra had been instrumental in recognizing the object's unusual nature. It wasn't quite awe, though the sight was certainly awe-inspiring. It was something closer to vertigo. A feeling of foundations shifting, of everything that had seemed solid and certain suddenly revealed as contingent and temporary. We were not alone. We had never been alone. The universe contained other minds, other builders, other seekers. And one of their creations had visited our corner of space, had drifted past our planet while we were still hunter-gatherers, and was now departing back into the deep cosmic dark having delivered a message we were only beginning to comprehend. You are not unique. The capacity to question and explore and build is written into the structure of reality itself. Others have walked this path before you, and the galaxy is a much stranger and more populated place than you imagined. The mission team spent the following weeks processing data, refining measurements, extracting every possible piece of information from the encounter observations, but the essential conclusions were clear from the first detailed images. 3. Atlas was artificial. It had been built. The materials weren't exotic, mostly iron and aluminum alloys, with traces of other elements, but their arrangement, their structure, the precision of their assembly, all spoke to deliberate design and manufacture. Some panels had markings that, when analyzed carefully, showed regular patterns at multiple scales, possibly some form of writing or symbolic notation. Whether these markings contained information that could be decoded, or whether they were merely decorative or functionally necessary for the object's construction, remained unclear. But their presence suggested that whoever built this object had some form of symbolic communication, some way of representing information visually. The narrow-band emissions, when analyzed in detail from the close-range data, showed characteristics of laser diodes, just as the earlier spectroscopic analysis had suggested. 3 small apertures on the cylinder's surface, spaced 120 degrees apart around its circumference, were emitting coherent light at the infrared wavelengths that had been detected from Earth. The purpose of these lasers was unknown, whether they served as beacons, rangefinders, communication systems, or had some other function, but their operation after such immense time spoke to remarkable engineering reliability. The thermal excess, that puzzling few degrees above equilibrium temperature, was traced to specific regions inside the cylinder where the spacecraft's infrared sensors detected slightly elevated heat flux. The object appeared to contain internal power systems, still functioning, still generating small amounts of electricity that kept the lasers operating and possibly powered other systems not yet understood. The radar data provided information about the object's internal structure, revealing that it wasn't solid throughout, but contained voids, chambers, regions of different density. This internal complexity suggested compartmentalization, perhaps different sections serving different functions, possibly still maintaining separate internal environments even after millennia of operation. Analysis of the micrometeoroid impacts on the surface allowed researchers to estimate exposure ages, calculating how long the object had been traveling through space based on the density and size distribution of impact craters. The answer aligned remarkably well with the trajectory analysis that had pointed toward HD 28343, approximately 50,000 years, give or take a few thousand years, of exposure to the interstellar medium and the sparse dust and micrometeoroids that fill interstellar space. This meant that 3I Atlas had been launched from the HD 28343 system roughly at the time when anatomically modern humans were spreading across Africa and the Middle East, when our species was young and our technology consisted of stone tools and fire and storytelling, while we were developing language and art and the cognitive capabilities that would eventually lead to civilization. This object was traveling through the dark between stars, crossing light years at a pace that seems impossibly slow by human standards, but which is, in cosmic terms, a respectable fraction of the galaxy's rotation speed. How long had the civilization that built it been gone? Were they still around their orange star in Perseus, still building probes and sending them to other systems? Or had they vanished millennia ago, destroyed by disaster or evolution or choice, leaving only their artifacts scattered through the galaxy as testaments to their existence? These questions had no answers. Not yet. Possibly not ever. But they became part of the conversation, part of the new framework humanity had to construct for understanding its place in the universe. The data from the 3I Atlas encounter was released publicly in stages, starting with the clearest evidence of artificiality and moving toward more detailed technical analyses. The first press conference, held at NASA headquarters on July 25, 2027, 3 days after closest approach, included just 3 images. A wide view of the entire cylinder showing its panels and appendages, a close-up of a particularly well-preserved panel showing its seams and markings, and an infrared image showing the 3 laser emission points glowing brightly against the cold background. The NASA administrator, flanked by the IORM mission director and several senior scientists, including Dr. Konstantin read a prepared statement. Today, we can confirm that the interstellar object designated 3I Atlas is of artificial origin. The spacecraft images reveal geometric structures, manufactured materials, and active systems that could not have formed through natural processes. While we cannot yet determine the object's precise purpose or origin civilization, we can say with confidence that it represents evidence of extraterrestrial technology. This is one of the most significant discoveries in human history, and we are committed to sharing all data and analyses with the global scientific community and the public. The press conference was watched by over 1 billion people worldwide, according to estimates. The images were distributed through every news service, analyzed on every television channel, debated in every online forum. The confirmation that humans were not alone, that the universe contained other technological species, that we had detected one of their artifacts, was no longer speculation or hope or fear. It was established fact, supported by data, confirmed by observation, as real as any other scientific discovery. The weeks following the announcement saw intense activity across multiple domains. The scientific community mobilized to analyze the data, with hundreds of researchers working on different aspects of the object's structure, composition, and function. The SETI community renewed its searches with fresh urgency, targeting HD 28343 and other nearby stellar systems with unprecedented sensitivity. Philosophers and ethicists engaged in discussions about what the discovery meant for human identity, purpose, and future. Religious leaders offered interpretations ranging from confirmation of divine creation that extended beyond Earth to challenges to traditional theological frameworks that had assumed human uniqueness. Governments convened policy discussions about how to respond. Should humanity attempt to send a message toward HD 28343, even though the round-trip light travel time was 88 years and any response would be received by future generations? Should resources be allocated to developing interstellar travel capabilities now that we knew such travel was possible? What protocols should govern future encounters with extraterrestrial artifacts or signals? The questions were vast and complex and had no obvious answers, but they had to be addressed because the situation was real and present and required response. Dr. Loeb, vindicated in his long advocacy for taking artifact hypotheses seriously, wrote an essay titled, "Now What?", in which he argued that 3I Atlas should be seen not as an ending, but as a beginning. We have confirmed that we are not alone, but we still know almost nothing about our cosmic neighbors. We don't know how common technological civilizations are. We don't know how long they typically survive. We don't know if they communicate with each other or remain isolated. We don't know if 3I Atlas is one of millions of such probes scattered throughout the galaxy, or if it represents a rare exploratory effort by a vanished civilization. The data from 3I Atlas has answered one question. Are we alone, but has raised 1,000 others? Our task now is to pursue those questions with the same rigor and determination that allowed us to recognize 3I Atlas for what it was. As summer turned to fall in 2027, the intense public attention began to fade somewhat, though interest remained far higher than for typical astronomical discoveries. People returned to their daily lives, but with a subtle shift in perspective, a background awareness that the universe was populated, that somewhere out there, beings had looked at the stars and wondered and built things and sent them forth, just as we were beginning to do. 3I Atlas itself continued its journey outward, receding from the Sun at 42 kilometers per second, now beyond Neptune's orbit and still accelerating away under the Sun's diminishing gravitational pull. The spacecraft that had visited it was also receding, its mission complete, its power fading as its radioisotope generators slowly decayed. Eventually, Both objects would become too distant for communication, would pass beyond humanity's technological reach, would return to being invisible specks in the vast dark. But they had intersected, briefly, at this particular moment in human history, when we had just barely developed the capability to recognize and investigate such objects. Had 3I Atlas passed through our solar system a century earlier, we might have missed it entirely, lacking the telescopes and sensors to detect such a small, distant object. Had it arrived a century later, we would have been more prepared, with better instruments and faster spacecraft and deeper understanding. But it arrived when it did, and we responded as best we could with the tools we had, and we learned. Dr. Chen, reflecting on the entire experience in an interview with Scientific American, said something that would be quoted often in the years that followed. The thing about 3I Atlas that I keep coming back to is how close we came to missing it. If the spectroscopic observations had been scheduled differently, if the data pipeline had had a different bug that masked the emission peaks, if any of a dozen small decisions had gone another way, we might have cataloged it as just another interstellar asteroid and moved on. The object would have passed through our system and departed, and we'd never have known what we'd missed. That terrifies me and excites me in equal measure. It terrifies me because it suggests how much we might be missing, how many anomalies we might be overlooking because they don't fit our expectations. But it excites me because it means there's so much more to discover, so many more mysteries waiting for anyone who looks carefully enough. The detailed data analysis would continue for years, with papers being published describing specific aspects of the object's structure, composition, and behavior. The images would be studied at length, with researchers attempting to decode any information contained in the surface markings, trying to understand the function of various structural elements, modeling the internal systems and power sources. Some questions would be answered. Many would remain open, possibly forever, unless we someday developed the capability to build faster spacecraft that could chase down 3I Atlas and conduct longer, more detailed investigations. But the essential truth was established, confirmed, undeniable. The readings had pointed to artificial origin, and the close-range observations had proven it. Nature doesn't build cylinders covered in geometric panels with laser emitters and internal power systems and surface markings. Nature doesn't maintain rotational stability with millisecond precision across thousands of years. Nature doesn't launch objects on trajectories aligned with galactic coordinates toward other stellar systems. Someone had built this. Someone had engineered its systems, had launched it on its journey, had programmed it to continue transmitting even after immense time, had perhaps hoped that someday, somewhere, other beings would detect it and recognize it for what it was. And we had seen it, had studied it, had sent a spacecraft to examine it, had documented its existence and characteristics and shared that knowledge with our entire species. In the quiet hours after midnight, when the press conferences were over and the data was being analyzed and the public had moved on to other news, a small group of researchers who had been involved with 3I Atlas from the beginning gathered informally to discuss what it all meant. They sat in someone's office at Caltech, eating takeout food and drinking coffee, and talked about the journey they'd been on for the past 2 years. Dr. Chen described the moment she first saw the emission peaks and knew something was wrong, knew the spectrum didn't make sense. Dr. Talbot talked about running the trajectory backward and seeing it point toward HD 28343, and the strange feeling of recognizing that this object had come from somewhere specific, had been traveling toward us for longer than human civilization had existed. Dr. Santos discussed the radar echoes and how the geometric regularity had been obvious in the data long before anyone wanted to acknowledge what it implied. Dr. Constantine remembered writing that memo, using the word engineered, knowing it would be controversial but feeling obligated to call things what they appeared to be. And they talked about what came next, about the other searches that were being conducted, looking for additional interstellar objects that might show similar characteristics, about the missions being planned to investigate other anomalies in our solar system, unusual comets, asteroids with peculiar orbits, objects that might reward closer inspection. About the expanded SETI efforts, now that we knew technological civilizations existed and built things that crossed interstellar distances. About the long-term vision of humanity becoming an interstellar species ourselves, building our own probes, sending them to other stars, perhaps someday encountering artifacts from other civilizations as we explored the galaxy. But mostly they talked about the feeling of that moment when the first detailed images arrived, when they saw those panels and knew, finally, definitively, that we were not alone. It was a feeling that would fade with time, that would become normalized as the discovery was integrated into our understanding of reality. But in that moment, in those first hours and days after confirmation, it had been profound and transformative and overwhelming. We live in a universe where minds emerge, Dr. Constantine said quietly, where matter organizes itself into structures that can observe and question and understand. And we live in a universe where those minds, when they emerge, look outward and wonder about others and reach out across impossible distances to make contact. 3. iAtlas proves that. It proves that the impulse to explore, to send something of yourself into the vast unknown, isn't uniquely human. It's written into the nature of intelligence itself. And that means... She paused, searching for words. That means we're part of something larger, some cosmic community of questioners and builders and explorers. We don't know how large. Don't know who else is out there. Don't know if we'll ever meet them. But we're not alone in asking these questions. And that matters. That matters more than almost anything. The others nodded, and for a while no one spoke, each lost in their own thoughts about what had been discovered and what it meant and what humanity would do with this knowledge in the years and decades and centuries to come. Outside, the stars shone with their usual indifference, as they had for billions of years before Earth formed, and as they would for billions of years after Earth was gone. But now, looking up at those stars, humanity knew what previous generations had only suspected or hoped. We were not alone in looking back. Somewhere out there, around an orange star and Perseus, or perhaps around millions of other stars and millions of other systems, others had looked up and wondered and built and sent forth their creations to explore the vast cosmic ocean. And one of those creations had visited us, had passed through our solar system, had been recognized and investigated and understood. The data was clear, the math impossible. Nature doesn't build precision like this. Someone or something does. And in recognizing that fact, in confirming it through observation and analysis and the hard work of scientific investigation, humanity had taken its first step toward understanding its place in a populated galaxy. The readings had pointed to artificial origin. The mission had confirmed it, and now, the long process of learning to live with that knowledge, of integrating it into our understanding of ourselves and our future, could begin. In the end, that was perhaps the most important discovery of all. Not just that 3 iAtlas was artificial, but that we had been capable of recognizing it, of marshaling the resources and expertise to investigate it, of approaching the question with rigor and skepticism and openness. We had been capable of changing our minds when the evidence demanded it, of entertaining extraordinary hypotheses when ordinary ones failed, of doing science the way it's meant to be done, following the data wherever it led, even when it led to conclusions that challenged everything we thought we knew. That capability, that willingness to question and investigate and accept uncomfortable truths would serve humanity well in the years ahead. Because 3 iAtlas was not an ending. It was a beginning, a doorway opening onto vistas we had only imagined, a confirmation that the universe was stranger and richer and more wondrous than we had dared to hope. The object itself would continue its journey, departing our solar system, returning to the interstellar medium, traveling on toward whatever destinations lay along its path. Perhaps it would pass through other stellar systems, perhaps be detected by other civilizations at different stages of development, perhaps continue transmitting its narrowband signals for thousands of years more until its power finally failed and it went dark and silent and dead. Or perhaps not. Perhaps somewhere in its ancient programming was a directive that would activate new systems, begin new phases of its mission, adapt to circumstances in ways we couldn't predict. We didn't know. We couldn't know. Not yet. But we could watch and wait and continue studying the data we had gathered and prepare for the possibility that someday we might detect another object like 3I Atlas, another artifact from another civilization, another piece of evidence that the cosmos was not empty and cold and lifeless, but rather alive with minds and purposes and stories. And when that day came, whenever it came, we would be ready, because we had done this once before. We had recognized an anomaly for what it was. We had investigated it properly. We had confirmed the extraordinary through the ordinary methods of science, and we had changed fundamentally and permanently our understanding of our place in the universe. The data was clear, the math impossible. Nature doesn't build precision like this. Someone or something does. And knowing that, we could no longer look at the night sky the same way. Every star was now a possibility. Every dark patch between stars might hide travelers like 3I Atlas, ancient artifacts from ancient civilizations, messengers from minds we had never met and might never meet, but who had looked at the universe and done what we were learning to do. They had asked questions, had built things, had sent them forth into the unknown, hoping that someday someone would find them and understand. We had found one. We had understood. And in doing so, we had joined, at last, that community of cosmic questioners that had always been there, waiting for us to develop the capability to recognize our membership. The long night of human isolation was over. The conversation, however slow and difficult and mediated by vast distances and vast time spans, had begun, and nothing would ever be quite the same again.